Everyone, welcome to HIT Classroom about electrical circuits fundamentals. Today, we are going to talk about how to solve a complex circuits using Kirchhoff's law. Okay, let's break down Kirchhoff's law in a simple way. These are like the golden rules for how electricity moves in circuits. We've got two main ideas to cover, one about current and one about voltage. First, Kirchhoff's current law. The algebraic sum of currents in a network of conductors meet at a node is zero. Think of it like a busy intersection where wires come together. That's what we call a node. This law says the current flow in and out of that spot has to balance out perfectly. Picture traffic at a junction. Whatever comes in has to match what goes out. So when we add it all up, it equals zero. Here's the trick. We give currents a sign, positive if they are flowing in, negative if they are flowing out. For example, here at node A, we can say something like I2 plus I3 equals I1 plus I4, or we could write it as I2 plus I3 minus I1 minus I4 equals 0. But we don't write current equations in this form a lot. Easy enough, right? Now let's talk about Kirchhoff's voltage law. The directed sum of the voltage around any closed loop is zero. Imagine a closed loop in your circuits.
Okay, here we have a simple circuits. Now let's see how we can use the Kirchhoff's laws to solve it. And first, let's see what kind of elements we have here. And first we have a battery here. And we have three loads. Resistor 1, 2. Okay, so the first step. For the first step, first we need to label out all the nodes here. To my habit, I always note it clockwise. A, B, C, D, E, F. Once we have all the nodes labeled out, the next step, we need to identify all the currents and voltage involved in these circuits. First, let's see the battery has its positive ends up, which means the current should flow out from this end. So the current going through the R1 should be in this direction. We number it as I1. And once the current come into the node B, then it will split into two branches, and one going in this direction and going through the R2, then we call it I2. The other one will go into this direction, it will go through R3, and we can number it as I3. Okay, we can see that here we usually number the current based on the resistor it go involved in these parts. Once we complete all the labeling of current, now let's label the voltage. Here, the first voltage is the battery. So the battery has an output with a level of E, which go in with a polarity like this, positive up and negative down. And then the current going through the R1, then over the R1 we have the voltage V1 and current going from the positive parts to the negative parts. Then here for the R2, current going from up down here. And then we have the voltage over it as V2, current going from the positive to the negative. Similarly, we get the voltage over the V3 as this. So the current will flow from the positive to the negative. Okay, at this point, we have all the current labeled out. Then the next step is we need to write some equations based on the Kirchhoff's laws. So how we should do the equations? First, let's go with the voltage equations. Let's recall, based on the Kirchhoff's law, the sum of all the voltage drops in a closed loop should be equal to 0. First, we need to identify the closed loop. The first loop we can find is here. So it's from A, B, E, F, this loop. A, B, E, F. Here we can see that there are 3 components involved in this loop. Battery here, R1 and R2. Then we can write the equation as E equal to V1 plus V2. And apparently the V1 equal to I1 times R1 and V2 equal to I2 times R2. Then we have equal to I1 times I2, R1, I2 times R2. Now we have our equation 1. Okay, so any other loops here? Okay, we can find a small loop here, and it involves 2 elements. One is R2 and R3. And then we can see, and they have opposite direction with the voltage. Then this loop we can call it B, C, D, E. B, C, D, E. Here we can find that because they have the same terminal, then which means the V1 equals to V2. And similarly, V2 equal to V3. Similarly, so V2 equal to I2 times R2, so it's I2 R2 equal to I3 R3. Okay, then we have our equation 2. Okay, then it looks like we have all the loops considered here. And then now let's move on to the currents. So let's recall that for the Kirchhoff's law about the current, it means and any node, all the currents flow into this node should be equal to all the currents flowing out of this node, which means we need to identify or find a node which can involve multiple currents. Here, let's see, the one we need to pick in this equation is the node B here. Because why we pick this one is because in node B, we have current I1 flow into it, I2 and I3 flow out. So this node, it interacts with all 3 currents here. So based on the Kirchhoff law, we go with B. Then we have I1, all the current flow in, it should be equal to all the current flow out. Then we have our equation 3. Okay, now let's see. If we assume we know the voltage provided by the battery or the resistance for the resistors here, the only thing we need to solve here is I1, I2, and I3. And here we have 3 unknown and 3 equations, which means we can solve it. How to solve it? First, we need to do a lot of substitutions. First, we need to eliminate some current. And here we can substitute the equation 3 into equation 1. Then we have E equal to I2 plus I3, which replaces the I1, and times R1 plus I2 R2. And we can expand it a little bit. R1 plus I3 R1 plus I2 R2. Okay, here we can see that in this equation we have I2, I3, I2. So we have 2 unknown. To solve it, we need to eliminate at least one of those. So then how we can eliminate? Then we have to use the equation 2 here. Here, I2 R2 equal to I3 R3 means we can find the relation between I3 and R2 like I3 equal to I2 R2 over I3. Here, we can put this one into here, then we have equal to continue to solve this equation is I2 R2 over R3 R1 plus I2 R2. Okay, we replace the I3 with expression with I2. Then we can see here we only unknown here is I2, then we have the I2 equal solved out is equal to E over R1 plus I2 R2 over R3 times R1 and plus, I'm sorry, here we shouldn't like this one, and R2. Okay, since we know we have the electrical output, the voltage output of the battery, we have the resistance for all the resistors, then we can solve the I2 easily. And we once have the I2 solved out, then we can put it back here, then we can solve the I3. Once the I3 and I2 are solved out, we can put them back here. Then we can have the I1 solved out. Okay, simple, right? It's pretty straightforward. And once we have I1, I2, I3 solved out, then it's easy to find out the way 1, way 2, and way 3.
Alright, let's walk through how to solve circuits using Kirchhoff's law step by step. Super simple. First, we label all the nodes, the spots where wires connect, with letters like A, B, C, D, and so on. Next, we figure out all the currents and the voltage, giving them numbers based on the resistors they are tied to. Third, we write down equations using Kirchhoff's laws. For this, we will pick out closed loops for the voltage equations and find the K nodes where multiple currents meet for the current equations. Finally, we solve those equations by plugging one into another to figure out the unknowns. That's it. Nice and straightforward.
Alright, let's solve this circuit using Kirchhoff's law. Here we've got 2 batteries, E1, E2, and 3 resistors, R1, R2, R3. All of them have values assigned, so we are ready to go. First thing first, we label all the nodes. Remember, I like going clockwise, so A, B, C, D, E, F, G, H. Next, we figure out all the currents and the voltages. Let's start with the battery. We've got 2, E1 and E2, and we'll pick E1 as the main one since it's got the bigger voltage. The positive end of E1 is at the top, so the current I1 should flow in this direction. Since it goes through R1, so we call it I1 here. When it reaches node B, it splits. One part going through the R2, we call it I2, and the other one heads towards node C, we call it IBC. And node C, IBC split again. I3 goes through R3 and I4 loops back to E2. So we've got all our currents mapped out, I1, I2, I3, I4. Now let's go with the voltage, starting with E1 again. Since its positive end is at the top, the voltage is positive up and negative down here. Across R1, the voltage 1 should also have the current flowing from the positive to the negative. Same deal with the R2. I2 will flow in from positive to the negative. The R3 will follow the same pattern here, positive up and negative down because the current going this way. Okay, finally, E2 has its positive ends at the top, so it has the positive up and negative down here. Easy so far, right? With current and voltage labeled, let's write some equations using Kirchhoff's law. First up, the voltage law. It says all the voltages in a closed loop add up to 0. So let's find a loop. Start at A, go through B, G, and back to H. That's the A, B, J, H loop. In this loop, we've got E1 pushing voltage up, while R1, R2 drop it. Since they are in opposite directions, we can write E1 equal to V1 plus V2. Since V equal to IR, so we can write it as I1 R1 plus I2 R2. This is our first equation. But we still need to get R3 and E2 to include. So let's find another loop. How about the BCFE? FG. In this loop, we've got R2 and R3 and their voltage are positive each other, so we have V2 equal to V3, and we can rewrite it as I2 R2 equal to I3 R3. We have our second equation. One more loop. C, D, E, F. Here we have R3 and E2 with opposite polarity. So we have V3 equal to E2. And we can rewrite it as I3 R3 equal to E2. This is our third equation. Now let's switch to the current law. It says all currents flow into a node equal the currents flowing out. Here, node B is our star because it's super busy. I1 flows in and I2 plus IBC flow out. Since IBC splits into I3 and I4, then we can write for the node B, I1 equal to I2 plus IBC. IBC is I3 plus I4. Then we have it equal to I2 plus I3 plus I4. Then this is our fourth equation. We've got four equations now, 3 for voltage, 1 for current, and it's time to solve. Since we've got some values, let's start with equation 3 here. I3 times R3 equal to E2. Then for the equation 3, we can find the I3 equal to E2 over R3, and it equal to 6 over 24, and it's 0.25 amp. Okay, once we get the I3 figured out, then we can find that the equation 2 can be solved. Here we have equation 2, then we find I2 equal to I3 R3 over R2. Then we have 0.25 times 24 over 12, it should be 0.5 amp. Okay, now we have I2, then we find that the equation 1 can be solved. Then we have it, equation 1 here, then it I1 equal to E1 minus I2 R2 over R1. Then we have it 12 minus 0.5 times 12 over 12. Okay, then we have 0.5 amp for I1. So we have I1, I2, I3, then it's easy to figure out I4 here. So using the equation 4, I4 equals to I1 minus I2 minus I3 equal to 0.5 minus 0.5 minus 0.25, then we have it equal to negative 0.25 amp. Negative? So no worries, it just means I4 flows the opposite way. It shouldn't go this way, instead it should go the back. It should from the E2 and back into the circuits in this way. Okay, here we go. We have I1 equal to 0.5 amp, I2 equal to 0.5 amp, I3 is 0.25 amp, and I4 is negative 0.25. Okay, here you can see that it's simple, right? So we just label the nodes, find the currents and the voltages, write equations, and then solve.
Okay, that's all for today. See you next class.